Hey guys, so in this video we are going to be talking about operators. And we've talked about operators extensively in section 2, and now what we're going to do is take the way we formulated operators back in section 2 with the vector Hilbert spaces and take them now in, just like everything else we've been doing, take it from the vector Hilbert spaces into now our continuous function Hilbert space. And so if you remember, hopefully you remember what operators do. They have the eigenvalue equations, which we'll talk more about in the next video. But in this video, we're going to talk about Hermitian operators, right? First of all, linear operators still hold. If you remember, linear operators had the conditions where if you had some linear operator, I'll call it L hat on A plus B, right? This is L hat on A plus L hat on B. That's a linear operator. And the other part of it is L hat on C times A, where C is some scalar, some constant. This is C times L hat acting on A. You can take constants outside of, or scalar constants outside of a linear operator. So that's linear operators. Now we're looking at a special type of linear operator, right? Hermitian operators are linear. We've talked about Hermitian operators before. I'd like to go a little bit more in depth on them in terms of function spaces because we haven't really gotten to what a Hermitian operator and function space is. And so to remind you why we're doing this, right? Why Hermitian operators are important anyways, right? It turns out, for very logical reasons, any operator in quantum mechanics representing a physical variable has to be Hermitian. And it's because of these three key properties of Hermitian operators at the bottom. I proved two of them, and one of them requires a bit more linear algebra to prove, but I think in the video in section 2 about this, I attached a proof to that. So the first thing is Hermitian operators have real eigenvalues, and if we're representing an observable with an operator, the eigenvalue is the value of the observable, right? Hopefully you remembered that, or you can go back to section 2 and look at that. And it's important that any real observable has any physical observable has real values that it takes on. We can't have an imaginary momentum or an imaginary position, right? That's not how it works. So we have to have operators with real eigenvalues to represent physical observables. Second is the eigenstates or eigenfunctions or eigenvectors, right? These are all kind of interchangeable. You know, the functions are in function space, vectors are in vector space, but in general they're all eigenstates. The eigenstates are orthogonal. This was really important because we had this one of our postulates of quantum mechanics was that if you take the inner product of say if you take like the inner product of psi, actually I think we do this the other way around. Take the inner product of phi sub q and psi, we get, and we take the norm square of this, we get the probability of having q, the observable q, being equal to this little q, right? And if we have, if psi is, say, a different state, so this is, say this is q1, So, all right, first of all, this is the probability if a particle is in the state psi, it has big Q equal to little q, right? Well, what if the state psi, so if psi is phi sub q2, right, and this is like phi sub q1 here, right? If psi is phi sub q2, then the probability of being in the state with a value of big Q being Q2, the probability if you're in that state of having Q equal to Q1 has got to be 0, right? So therefore, phi Q1, phi Q2 has to be 0 if Q1 does not equal Q2. Right? And we've talked a lot about that condition. But that is a condition that is guaranteed if we're looking at the eigenstates of Hermitian operators, right? And so for quantum mechanics to work, the eigenstates have to be orthogonal, and so therefore we've got to be working with Hermitian operators. The other one is any state, right, or any wave function can be written as a superposition of eigenstates, which is really important, right? Because if, say, we have a basis of all the possible momentum states, right, we have to be able to construct the state of the particle as some superposition of having this momentum and this momentum and this momentum, right? You can't have any other parts to it. The entire wave function has to be able to be described by the spectrum of allowed values for the energy or the momentum or the, right? That just makes sense that we should be able to have that. So because of these properties, we have to be dealing with Hermitian operators. So that is why this is really worthwhile to talk about. So now we go on to the definition of a Hermitian operator. So Q hat is Hermitian if this statement with inner products is true for any normalized wave function psi1 and psi2. And so this is also saying that the Hermitian conjugate of Q hat is equal to Q hat, right? Because this statement is true right here. And I'm going to write this in our integral notation just to get us sort of used to that. So this statement, I'll circle this in green. This statement I'll write in its integral form, the integral from negative infinity to infinity, psi1 complex conjugate times Q hat psi2 dx, right, is equal to the integral from negative infinity to infinity of Q hat psi1 complex conjugate psi2, right? It's not just Q hat, it's Q hat dagger. Hopefully you caught that. It's not just Q hat acting on psi1, right? It's not just Q hat dagger acting on psi1 star. It's Q hat dagger acting on psi1, then that you take the complex conjugate, and then there's a dx here. That's sort of like saying, and I hope I didn't do this wrong in previous videos, and if I did, I apologize, but now you'll know the right way. So if we have, let's see, the bra vector Q hat psi, right? This is Q hat acting on psi, right? This is Q hat acting on psi, all of that Hermitian conjugated, right? So that's sort of what's going on here, right? So then this ends up being Q hat, right? Oh, well, yeah. So then if this is Q hat dagger, right, like it is in this equation, this would be Q hat dagger right here. That's probably the best way to explain it. So hopefully this makes sense, right? If this thing is equal to that, right? And in this case, we have a complex conjugate because this is the vector. Okay, so it's a function in this case. It's the complex conjugate, and because that's how we define the inner product. Hopefully that's not confusing. If it is, just take this as a mathematical definition. But hopefully it should make at least a little bit of intuitive sense. So now we're at the final part of this video, which is what operators are Hermitian. And I have four different operators that we are going to quickly test this out with. So I'm going to go with number one. I'm going to write them down here, and we're going to test if they are Hermitian or not. So I'll put a check or an X. Right? Number one is is multiplication by a real number. Or by a real, not necessarily just a number. I mean, it's a real scalar. Right? Or, a real scalar slash a real function. Right, and it's a scalar valued function, right? So it doesn't just have to be a number. It doesn't have to be multiplying by 2. It can be multiplying by x as long as x is a real number, or x squared as long as x is real, right? Number 2, we'll look at multiplication by a complex scalar or function. Okay? 3 will be a derivative, right? And actually, those will be the first 3, and then I'll get to the last one right after. It will kind of fall out kind of naturally based on the results of these. And so then, first notice that these are all linear operators, right? So we're only testing this with linear operators. I'll guarantee for you that x squared, or sorry, not x squared, the squaring operator, the s hat, is not Hermitian. It's not linear, so it's not going to be Hermitian. It won't be able to follow this property, and you can prove that yourself. So the question is if this is true. And actually, we'll work with one side of this. So what we're trying to prove is this thing right here. This is what we want to prove. Right? Okay. So let's take the integral. Let's start with multiplication by a real scalar function. These are all integrals from, actually I'll leave that in, negative infinity to infinity. Okay. Negative infinity to infinity of some real function. I'll call it f of x. Or actually, I'm just gonna call it. I'll just call it f. Okay. Where f is real. Okay. So f times what we're looking at this first one. So it's going to be psi 1 star times f psi 2. Right? Well, we can actually move this around, right? Because multiplication is commutative, at least with functions, right? These are functions. So multiplication is commutative. So this will be equal to negative infinity to infinity f times psi 1 star times psi 2 dx. And this happens to be the same thing as f psi 1 star, times psi 2 dx. Right? Why is this true? Because if we remember, the complex conjugate will distribute when you're multiplying, and so this will be f star times psi 1 star, but f star equals f, right? And so therefore, this is equal to this, which is what we want to show. So this is Hermitian, multiplying by a real scalar function. So now I'm going to keep most of this actually to switch this for a complex function, and maybe you actually see where this proof is going, and if you do, maybe try to pause this video and do it yourself. I'll do this right now. I'm just going to relabel our function f as, we'll call it z. Actually, I don't want this. So z is not necessarily real. Okay. So psi1 star times z psi2 equals, well, again, still with complex numbers, it's still commutative. Now, what this is this happens to be the same thing as the integral from negative infinity to infinity of z star psi1 psi2 dx, right? And this is not necessarily the same as the integral from negative infinity to infinity of z psi1 star psi2, right? Not necessarily the same, because z star does not have to be equal to z. Z is not necessarily real. So multiplication by a complex scalar function is not Hermitian. However, we can actually figure out what the Hermitian conjugate of multiplication by a complex number. This actually shows that the Hermitian conjugate of z, of some complex function, is z star, right? Because it fits, oh, and I actually did forget the star here, so hopefully you caught that. This is not equal to the integral from negative infinity to infinity of z star psi1 star psi2. Hopefully you did catch that. Okay. So now, going back to just this this line here, if I erase this line here, this shows you, in fact, right? Because if you match it up with this, psi1 times q hat, psi1 inner product with q hat psi2 is q hat dagger psi1 complex conjugate times psi2, right? So by just comparing this and looking at the integral definition of this equation, hopefully you wrote that down. If not, go back, write it down, compare it to this, right? And you'll see, in fact, something pretty cool. Z Hermitian conjugate is equal to z star. Okay, so we're going to go back and use that. Okay, now, finally, we are at the derivative. And this one, you might think, oh, the derivative is real, right? How could its Hermitian conjugate? I mean, its complex conjugate is itself, right? If just taking a derivative is a real thing. So, you would think, how could this possibly be not Hermitian? So let's see if it is. This is equal to, so this is what we're looking at, right? Well, in fact, there is something, right, when you're taking something, the integral of some psi1 times psi1 star times the derivative of psi2, there's actually a formula for this. Maybe you are familiar with integration by parts. If not, I mentioned in the video, one of the videos on integration, and just take this formula to use it. I'll write it down over here. The integral from a to b of g of x times the derivative of f of x dx equals f of x times g of x evaluated from a to b minus the integral from negative infinity to infinity. Or, sorry, not from negative infinity to infinity. I'm getting ahead of myself there. Minus the integral, same bounds, from a to b of f of x times the derivative of g of x called integration by parts. And what we're going to do is we're actually going to apply this here. So this is equal to the, well, first let's go, right, if we just match that up with this equation, we know g of x is psi 1 star and f of x is psi 2. So this is equal to, I'm doing this in white, so this is psi 1 star, psi 2, it doesn't matter which order, right, evaluated from negative infinity to infinity, minus the integral from negative infinity to infinity of psi 2. Actually, I'll write it like this, actually. Of d by dx of psi 1 star, this times psi 2 dx. Right? Now, first of all, this, because of normalization, we know that psi 1 and psi 2, and therefore psi 1 star, right, has to go to 0 at negative infinity and infinity, right? Because they're normalized. And remember, this is the definition for any normalized wave function. That's the Hilbert space that we're working on. We're working with normalized wave functions. So this part, right, if you plug in positive infinity, psi 1 star is going to be 0 and psi 2 is going to be 0, because they have to be, in order to be normalized, the wave function has to go to 0 at positive and negative infinity. Otherwise, you can't take the area under its magnitude squared from negative infinity to infinity, right? And same thing, if you plug in negative infinity, you'll get 0. So if you plug in this in at infinity and then subtract plugging it in at negative infinity, you get 0 minus 0 equals 0. So this thing actually equals 0. So now all we are left with is this integral. And in fact, if you you can take this derivative inside of the complex conjugate, because it is true that, and I'll write this just on the side here. It is true. Hopefully, I have space and some color. That the derivative of f star is equal to the derivative of f, all of that, star. This is a true property, right? Because the derivative is a real operator. This is not necessarily with the Hermitian conjugate. This is just with the complex conjugate. This is one of the places where we start to see the difference between the Hermitian conjugate and the complex conjugate. When you take things like that are not just numbers, when you take things like the derivative operator. And if we do this and then bring the negative inside that, you'll see why. This is equal to the integral from negative infinity to infinity of negative d by dx psi 1, all that star, psi 2 dx. Right? And is this equal to d by dx psi 1 star psi 2? No, it's actually the negative. So you can actually even say that a derivative d by dx Hermitian conjugate is equal to negative itself. Right? So the derivative is not Hermitian, right? The derivative is not Hermitian. In fact, its Hermitian conjugate is negative of itself. Now we're going to get to a quick fourth one. So we're going to, I'm going to erase this, hopefully have all of this written down, all these proofs. And now that I think about it, I think I'll break this last one up into two parts. So where C is real, note that C is real, I'm going to look at number 4, number 5, right? Where number 4 is going to be some constant times the derivative, okay? And number 5 is I times some constant times the derivative, okay? And now it is important to remember a property, and we'll go more in depth of this and show a little bit more technically correct how this property is in section 5. But for right now, the property that we are going to deal with is that if I have two operators, say Q hat and W hat, Hermitian conjugate, that's Q hat, Hermitian conjugate, W hat, Hermitian conjugate. And if you've done linear algebra and you know this is technically incorrect, just bear with me, because it's, for all intents and purposes, this is correct up until we get to chapter 5, or section 5, and then we'll refine this to make it a little bit more correct. And so, so given this, right, if we take C times d by dx, take its Hermitian conjugate, right? This is C Hermitian conjugate times d by dx, Hermitian conjugate. C Hermitian conjugate is C, because it's real. D by dx Hermitian conjugate is negative itself, so this is negative C d by dx. So, the C times d by dx, where C is real, is not Hermitian, right? The Hermitian conjugate, C d by dx, Hermitian conjugate, is equal to negative C d by dx. And just so you know, you can actually prove this property with the integral definition. You can prove this property. In general, without the integral definition, and with vectors, the property is not exactly correct. But if you would like to, you can take my word on it, or you can go and prove it. Lastly, number 5. If I have I times C times d by dx, right, and that property can be generalized to however many operators, right? Hermitian conjugate. This is, we'll do, let's see, I Hermitian conjugate times C d by dx, Hermitian conjugate, right? Now, I Hermitian conjugate is negative I, because it's the complex conjugate of, right, because by property number 2, or by operator number 2, and C d by dx dagger is negative C d by dx, right? And so we get, this is equal to I, because the negatives cancel, so I C d by dx. Turns out I times some constant times the derivative is a Hermitian operator, and this is going to be very, very important. So, just to recap what that means, is that we have the integral from negative infinity to infinity of psi 1 star psi 2 dx, or sorry, not, I meant times I C d by dx psi 2 dx equals the integral from negative infinity to infinity I C d by dx psi 1, this complex conjugate, times psi 2 dx. And you can actually prove this if you would like to using integration by parts, just noting that when you take the complex conjugate, you'll get a negative I over here, and then you can prove this statement. Okay, so I will see you in the next video.